Section: Introduction. We're living in an era where machine learning applications are growing rapidly. A key goal is to make the process of drawing conclusions from these applications efficient in terms of computing power and memory usage. Companies like NVIDIA and Amazon estimate that 80 to 90% of machine learning work is spent on this process, known as inference. With the rise of devices with low memory and computing power, like IoT devices, and the increasing popularity of attention mechanisms, there's a strong push to design more efficient attention mechanisms for inference. One popular method is cross-attention, CA, which retrieves relevant information from a set of context tokens during inference. However, CA scales linearly with the number of context tokens, which can be inefficient as many of these tokens are not needed. General-purpose architectures like Perceiver I/O try to make inference more efficient by first condensing the contextual information into a smaller, fixed-sized set of latent tokens. But this approach has its own problems. For one, problems with high intrinsic dimensionality naturally require a large number of latents. Secondly, the number of latents, which determines the capacity of the inference model, is a hyperparameter that needs to be specified before training. This can be problematic in practical situations where the required model's capacity may not be known in advance. In this paper, we propose two solutions. The first is tree cross-attention, TCA, a replacement for cross-attention that retrieves information in a way that scales logarithmically with the number of tokens. TCA organizes the tokens into a tree structure and retrieves information via tree search, starting from the root. This allows TCA to selectively choose the information to retrieve from the tree based on a query feature vector. TCA uses reinforcement learning to learn good representations for the internal nodes of the tree. Our second proposal is ReTreever, a flexible architecture that achieves token-efficient inference. In our experiments, we found that TCA performs as well as cross-attention while only requiring a logarithmic number of tokens. ReTreever outperforms Perceiver I/O on various classification and uncertainty estimation tasks while using the same number of tokens. ReTreever's optimization objective can leverage non-differentiable objectives such as classification accuracy, and TCA's memory usage scales logarithmically with the number of tokens, unlike cross-attention which scales linearly. Now, let's delve into the background of our work. Attention is a process that retrieves information from a context set. In this paper, we focus on cross-attention, where the goal is to retrieve information from the set of context tokens given query feature vectors. Reinforcement learning involves optimizing a policy that maximizes the expected discounted return. We use this in our proposed tree cross-attention, TCA, a token-efficient variant of cross-attention. TCA is composed of three phases: tree construction, retrieval, and cross-attention. In the tree construction phase, TCA organizes the context tokens into a tree structure. The retrieval and cross-attention phases are performed multiple times at inference time. After describing the phases of TCA, we introduce ReTreever, a general architecture for token-efficient inference. We provide a detailed illustration of the architecture of tree cross-attention and ReTreever. Section Summary. In this section, the authors discuss the need for efficient attention mechanisms in machine learning inference, particularly in low-memory, compute domains. They propose tree cross-attention, TCA, a token-efficient variant of cross-attention, which organizes context tokens into a tree structure and performs retrieval via tree search. They also introduce ReTreever, a flexible architecture that achieves token-efficient inference and outperforms existing methods on various tasks. Section: Tree construction. We're going to discuss how we build a tree structure to organize data tokens. This tree, let's call it T, is designed so that all the tokens are located at the leaves, or the endpoints of the tree. The nodes within the tree, which aren't leaves, hold a summary of the information from the nodes below them. This information is used for two main purposes: making predictions and retrieving specific nodes based on a query feature vector. The way we arrange the data within the tree is flexible. We can use prior knowledge about the data, simple rules of thumb, or even learn the best arrangement. Traditional tree algorithms, like ball tree or KD tree, can provide useful strategies for organizing the data. Once we've arranged the data in the tree, we use an aggregator function to combine the information from the tokens. This function starts at the parent nodes of the leaves and works its way up to the root of the tree, combining information as it goes. The process is like this. For each node, we take the information from all its child nodes and combine it using the aggregator function. This gives us a vector that represents the node. In our experiments, we used a balanced binary tree and a KD tree to organize the data. The KD tree splits the data evenly along an axis, using the median value. To keep the tree perfectly balanced, we add padding tokens that are ignored during computation. These padding nodes are fewer than the number of tokens, so they don't affect the overall complexity of the process. Next, we need to retrieve information from the tree. To do this, we use a policy learned through reinforcement learning to select a subset of nodes from the tree. The process starts at the root of the tree and selects one of the child nodes to explore further. The nodes that aren't selected are added to the set of selected nodes. This process is repeated until we reach a leaf node, which marks the end of the search. Because we're working with a balanced tree, the number of nodes we need to explore and retrieve is logarithmic, meaning it increases slowly as the size of the tree increases. The set of nodes we've retrieved is then used as input for a process called cross-attention, along with the query feature vector. This process has a logarithmic complexity, which is much more efficient than applying cross-attention to the full set of tokens, which has a linear complexity. The set of nodes we've selected covers the entire set of tokens, meaning every token is either part of the selected set or is a descendant of one of the selected nodes. Now, let's introduce ReTreever, a model that uses tree cross-attention to achieve efficient inference. This model is similar to the Perceiver I/O model, but with some key differences. While Perceiver I/O compresses information into a smaller set of latent tokens and then retrieves information from this set, ReTreever retrieves information directly from a tree structure. This makes ReTreever's inference process efficient regardless of the encoder used, and it scales logarithmically with the number of tokens. This means we can use a variety of encoders, such as a transformer encoder or more efficient versions like linformer or chord mixer. Section summary. The tokens in the data are organized in a tree structure, where internal nodes summarize the information of their subtree for predictions and retrieval. An aggregator function is used to aggregate token information from the leaves to the root of the tree. The retrieval process involves selecting nodes based on a learned policy, resulting in a logarithmic complexity. ReTreever is a model that leverages tree cross-attention for token-efficient inference, achieving logarithmic complexity regardless of the encoder used. Section: Training Objective. The section we're going to simplify and paraphrase is about the training objective of a model called ReTreever. This model's objective is made up of 3 parts, each with its own weight, represented by the symbols lambda_ca and lambda_rl. The first part, denoted as L_TCA, is about learning node representations in a tree structure. These representations summarize the relevant information in its subtree to make accurate predictions. The second part, L_RL, is about learning internal node representations for retrieval within the tree structure. This is done using a policy denoted as pi. The height of the tree, represented as log n, is the horizon. The symbol h stands for entropy, and r represents the reward or objective that ReTreever aims to maximize. Typically, this reward corresponds to the negative TCA loss, which can be negative MSE, log likelihood, or negative cross-entropy for regression, uncertainty estimation, and classification tasks, respectively. However, the reward doesn't need to be differentiable, meaning it can also be an objective that we usually can't optimize directly via gradient descent, like accuracy for classification tasks. The experiments aim to compare tree cross-attention, TCA, with cross-attention in terms of the number of tokens used and performance. This is done by comparing TCA and cross-attention directly on a memory retrieval task and by comparing ReTreever, which uses TCA, with models that use cross-attention. The experiments also compare the performances of ReTreever and Perceiver while using the same number of tokens. The analyses aim to highlight how ReTreever and TCA can optimize for non-differentiable objectives, show the importance of the different loss terms in the training objective, and empirically show the rate at which cross-attention and TCA memory grow with respect to the number of tokens. The benchmarks for these objectives are classification tasks like copy task and human activity, and uncertainty estimation settings like GP regression and image completion. The focus is on comparing TCA with cross-attention, and comparing ReTreever with general-purpose models like Perceiver I/O for the same number of latents and transformer, encoder, plus cross-attention. The results show that the baseline transformer plus cross-attention achieves results competitive with prior state-of-the-art. The results also show that Perceiver I/O requires several times more tokens to achieve comparable performance to ReTreever. In the copy task, the models are provided with a sequence of length n equals 2k, starting with the beginning of sequence boss token, followed by a randomly generated palindrome of 2k 2 digits, ending with an end of sequence EOS token. The task is to predict the second half of the sequence given the first half of the sequence as context. The model is evaluated on its accuracy on 3,200 randomly generated test sequences. The results show that both cross-attention and tree cross-attention were able to solve this task perfectly. However, TCA requires about 50 times fewer tokens than cross-attention. Perceiver I/O's performance was poor, further dropping as the length of the sequence increased. This is because Perceiver I/O tries to compress all the relevant information for any predictions into a small fixed-sized set of latents. But all the tokens are relevant depending on the queried index. So, methods which distill information to a lower dimensional space are insufficient. In contrast, TCA performs tree-based memory retrieval, selectively retrieving a small subset of tokens for predictions. Therefore, TCA is able to solve the task perfectly while using the same number of tokens as Perceiver. Section Summary. The training objective of ReTreever consists of three components. $L_TCA. Aims to learn node representations in the tree that summarize relevant information. $L_RL. Learns internal node representations for retrieval within the tree structure. And $L_CA. Optimizes for non-differentiable objectives. The experiments compare tree cross-attention, TCA, with cross-attention, highlight the optimization capabilities of ReTreever and TCA, and analyze the importance of different loss terms. Results show that TCA performs better than cross-attention and Perceiver I/O, achieving perfect accuracy with fewer tokens. Section. Uncertainty estimation, GP regression and image completion. We're going to discuss the performance of our model, ReTreever, in two different scenarios: Gaussian process, GP, regression and image completion. These are common settings for evaluating uncertainty estimation, and they've been widely used in the literature on neural processes. In the GP regression task, we're trying to model an unknown function using a set of points. During training, we generate these functions from a Gaussian process with a radial basis function, RBF, kernel. The kernel's hyperparameters are randomly chosen within certain ranges. After training, we evaluate the models based on the log likelihood of functions generated from Gaussian processes with RBF and Mattern 5/2 kernels. Our results show that ReTreever significantly outperforms Perceiver I/O while using the same number of tokens for inference. In fact, Perceiver I/O would need about 4.6 times the number of tokens to match ReTreever's performance. In the image completion task, we aim to predict the pixels of an image given a random subset of pixels. We use the Celeba dataset, which contains color images of celebrity faces. These images are downsized and the pixel values are rescaled. The number of pixels are randomly sampled within certain ranges. Unlike sequential data, where there's a clear way to split the data when constructing the tree, it's less clear how to do this with 2D image pixel data. So, we compared the performance of ReTreever using different methods for constructing the tree. These methods included organizing randomly, constructing the tree according to the first or second index of the image data, and constructing the tree using the value after a random projection. Our results show that ReTreever, when using any of these methods, significantly outperforms Perceiver. Interestingly, ReTreever uses about 21 times fewer tokens than Transformer plus cross-attention. ReTreever also uses reinforcement learning to learn good node representations for informative retrieval. But it's not limited to only using the learned policy for retrieval at inference time. For instance, we can choose to retrieve all the leaves of the tree, which we call ReTreever full. On both the Celeba and GP regression tasks, ReTreever full performs close to the state of the art. However, the standard ReTreever model achieves significantly lower results. This suggests that ReTreever's performance can vary depending on the number of nodes, tokens, selected from the tree. Therefore, an interesting area for future research could be the design of alternative methods for selecting subsets of nodes. Section Summary. In the section on uncertainty estimation, ReTreever outperforms perceiver I/O in GP regression and image completion tasks while using the same number of tokens for inference. In image completion, ReTreever with various heuristics for constructing the tree significantly outperforms perceiver, with ReTreever KD$X_0, ReTreever KD$X_1, and ReTreever KDRP performing the best. ReTreever Full achieves performance close to state-of-the-art on Celeba and GP regression, suggesting that the number of nodes selected from the tree can impact ReTreever's performance. Section: Time Series, Human Activity. We've been studying human activity using a dataset that includes 3D positions of the waist, chest, and ankles. This data was collected from 5 individuals performing various activities like walking, lying, and standing. After processing the data, we ended up with 6,554 sequences, each with 50 time points. Our goal was to classify each time point into one of 11 types of activities. Our results showed that our model, ReTreever, performed comparably to the transformer plus cross-attention model, but with 86% fewer tokens. Additionally, ReTreever significantly outperformed the perceiver I/O model while using the same number of tokens. We also analyzed memory usage and found that our tree cross-attention model was much more efficient than the cross-attention model. The memory usage of our model increased logarithmically with the number of tokens, while the cross-attention model's memory usage increased linearly. We also looked at the importance of different loss terms, specifically the cross-attention loss term and the RL loss term. We found that the RL loss term's weight was crucial for good performance, with a weight of 1.0 performing the best. If the weight was too small or too large, the model couldn't solve the task. The cross-attention loss term's weight improved the stability of the training, especially in the early stages. A weight of 1.0 also performed the best for this term. If the weight was too small, it caused some instability in the early stages of training, and if it was too large, it slowed down the training. In classification tasks, accuracy is usually the most important metric. However, accuracy is a non-differentiable objective, so in deep learning, we often use cross-entropy so we can optimize the model's parameters using gradient descent. But in the case of RL, the reward doesn't need to be differentiable. So, we compared the performance of ReTreever when optimizing for accuracy and negative cross-entropy. We found that using accuracy as the RL reward improved the model's performance compared to using negative cross-entropy. This is because accuracy is a simpler reward and easier for a policy to optimize. There have been a few previous studies that have proposed using a tree-based architecture for attention, the closest of which to our work is Treeformer. However, unlike these previous studies, we focused on replacing cross-attention with a tree-based cross-attention mechanism for efficient memory retrieval for inferences. Our model, TCA, learns a policy to select a subset of nodes, retrieves a subset of nodes with a full receptive field, and has a guaranteed logarithmic complexity. Our tree cross-attention model is similar to graph neural networks, GNNs, in that trees are a form of graphs. However, the objectives of GNNs and TCA are different. GNNs aim to perform edge, node, or graph predictions, while TCA aims to search the tree for a subset of nodes that is relevant for a query. Also, unlike GNNs which typically consider the tokens to correspond one-to-one with nodes of the graph, TCA only considers the leaves of the tree to be tokens.